Dear students of B.Tech first year, I am Dr. Rohin Parsai, Associate Professor of Mathematics in Engineering Science Humanity Department at Chamni Devi Group of Institution Indore. I will want to teach you through this lecture 7 of Unit 1 of Mathematics 2, examples of solution of higher order differential equations with constant coefficients. Let me see, this is first example on this topic. So first of all, whatever the question, if it is given to you, if it is of higher order with constant coefficient, just comparing with this standard form, on comparing the given equation with the standard form f of d over y equal to x, then you will find what will be the value of f of d and capital X. So f of d is d square minus 4d plus 3. Then for finding the complementary function, you will write the auxiliary equation. For writing auxiliary equation, on putting d equal to m in f of d and equate to 0, that is m square minus 4m plus 3 equal to 0. Then finding the roots, that is on factorizing this. So the factors of this, m square minus 4m minus m minus 3m plus 3, because 3 can be break into two parts in such a way that their product is this value plus 3 and their summation is minus 4. So that's why the factors are minus 1 and minus 3, that is m square minus m minus 3m plus 3 equal to 0. Now by taking first two terms m common, so we'll get m minus 1, and from second you will take minus 3 common, m minus 1. There is a common factor m minus 1, and the remaining factor is m minus 3 equal to 0, that is the possible values of m equal to 1 comma 3. Hence the roots nature are real and difference. Then in this case we write the complementary function as by taking first constant c1 e raised to m1x, means first root whatever may be given to you, and whatever may be the independent variables given to you is I am assuming that x is independent variables, you take x. So that's why c1 of e raised to m1 of x, that is 1 of x, plus c2 of e raised to 3 of x. Now since the x as a function of independent variables 0, so that's why the particular integral in such case is 0, that's why pi equal to 0. Hence the complete general solution of given problem is y equal to dependent variable equal to complementary function plus particular integral, that is you are just substituting the value of CF and pi, and the answer is c1 e raised to x plus c2 of e raised to 3x. Let me concentrate to the next example. Suppose this is a second question. Solve the equation d minus 2 whole square over y equal to 8 of e raised to 2x plus sin 2x plus x square. Now our first duty is to compare with this standard forms. Then by writing here f of d is d minus 2 whole square and capital X is 8 into e raised to 2x plus sin 2x plus x square. That is you are writing the auxiliary equation is m minus 2 ka whole square equal to 0. That is the possible values are m equal to 2 comma 2, which are real and equal roots. Then how can you write the complementary function? We know very well. So CF equal to c1 of plus c2 of x e raised to 2x. Now we will concentrate the finding the particular integral here. In general, the particular integral of this type of problems is defined by capital X upon f of d, that is equal to 8 into e raised to 2x sin 2x plus x square upon d minus 2 whole square. So now by separating this, 8 times e raised to 2x upon d minus 2 whole square sin 2x upon d minus 2 whole square plus x square upon d minus 2 whole square. So since in numerator you are having different functions, we have the different particular values of different particular integral. That's why I assume that the first term having particular integral denoted by p of I1, second term is p of I2, and third term suppose it is p of I3. Let me evaluate one by one all these three values here. That is, now first we concentrate on finding particular integral corresponding to e raised to tx. Is what do mean by the particular integral of exponential function is just obtained by putting in place of d equal to a. A means coefficient of e raised to x, whereas coefficient is exponential function power x, coefficient is 2. That's why you are putting in place of d equal to 2. So 2 minus 2 whole square, that is denominator is vanished. So numerator is a finite quantity and denominator is 0. Hence this method fails. We know that in that case, how can we resolve this case? So that's why therefore we resolve this case by the rule as e raised to 2x, keeping this multiply by x, and then differentiating denominator with respect to d. The differential of denominator with respect to d is twice into d minus 2, then into 1 into minus 0, that is simply this, and then you are putting this value of 2, you are getting again 0. So that's why you have to repeat this case of failure again. So multiply again by x, this gives to you x square e raised to 2x upon, then differentiate denominators with respect to d. Its differential is 1, that is 2 into 1, that is the answer is x square e raised to 2x upon 2. Similarly, you are going to find the particular integral corresponding to the next value here, sin 2x upon d minus 2 whole square. Just simplifying this by algebraic expansion, a minus b whole square. This gives to you a square means d square minus 2ab plus b square. Then in place of sine function you are putting d square equal to minus a square. So a is x coefficient, angle of this sine functions 2 ka square 4. So minus 4 plus 4 is cancelled out. Simply this gives to you minus 4 of d in the denominators. Now what do you mean by if you are having a numerator a function of x and denominator having differential operator? So what do you mean by inverse of differential operator? It means integration. So just you have to integrate by taking the constant multiple outside this. So minus 1 by 4 sin 2x of dx. Now you know that how you find the integral of this function very well. So by that you will get this integral is 1 by 8 times cos of 2x Now you concentrate the particular integral in the third phase as x square upon d minus 2 whole square equal to 1 by 4 of 1 minus d upon 2 whole raised to minus 2 or x square. So this is, now we know that what will be the expansion of the 1 minus x raised to minus 2 is, that's expansion you are applying here, 1 plus 2x, x is d by 2, so 1 plus 2 into d by 2 plus 3 into x square, that is d square upon 4 plus dot 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 up to x square. Since the power of this function is 2, so you will take first 3 terms. If degree is 4, you will take 4 plus 5 terms in this way in this expansion here. So now operating this inside this, so 1 into x square plus 2 into d upon 2 of x square plus 3 into d upon 4 of x square or this d square here having here. So this power 2 times when you differentiate, this gives to you 0. When you differentiate first time, you are getting 2 of d. So that is, you are getting the final answer here. So x square plus 2 into 2 upon 2 plus on differentiating this x square 2 times, this gives to you 3 into 2 upon 4 dot 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 here. And after simplification, this gives to you 1 by 4 of x square plus 2x plus 3 upon 2 to the 4, 3 upon 2. Now we can conclude here the particular integral as 8 times p of I1 plus p of I2 plus p of I3 just by adding all these. So this gives to you the integral values here. Hence the complete general solution is complementary function plus particular integral as y equal to, this gives to you the final answer here, c1 plus c2x e raised to 2x, so plus 8 times of this. Let me concentrate on other examples. As the third example, solve this equation again. We are given to you. I am discussing the various types of category of problems here through this lecture, so that you are able to solve the problems on this topic. So on comparing the given equation, first of all with this standard form, here you will get f of d equal to d square minus 2d plus 1 x equal to x e raised to x sin x. So now first of all you will write down the auxiliary equation m minus 2 a square minus 2ab plus b square. This gives to you the expansion of this. So the roots are m equal to 1 1, that is repeated roots again. So how can you write cf in this case, c1 plus c2x e raised to x. Now we concentrate the particular integral of this function. So x upon f of d, so e raised to x of x sin x upon f of d. So what is the role of e raised to x of v, x sin x assuming as v, so separate exponential function and d is replaced by d plus 1. So you are putting here in place of d plus 1. So just simplifying this gives to you e raised to x as it is x sin x upon d square. Then what do you mean by d square? It means you have to integrate this x sin x 2 times with respect to x. So on integrating first time with respect to x, this gives to you e raised to x of 1 upon d of x sin x dx. So e raised to x 1 upon d as it is. Now by applying the integration by parts formula, first function as it is into integral of second function, sin x का इंटीग्रेशन होता है माइनस cos x, तो माइनस x cos x एंड देन cos x का फिर से sin x होगा. इस तरह से आपको you are getting the second term integration is sin x, and now you are operating this again and again. फिर से इसका हम लोग 1 upon d करेंगे, means again you have to integrate second time here. So e raised to x as it is minus half integral of x cos x dx and integral of sin x dx. So now after integration this gives to you e raised to x of minus x sin x minus 2 cos x. Hence the complete general solution of this problem is to be obtained by the similar way, by writing dependent variable y equal to cf plus pi, c1 plus c2x e raised to x, and then plus e raised to x of minus x sin x minus 2 of cos x. Now we concentrate the next example, that is example number 4 here, on comparing the given equation with this f of d over y equal to x. Again you will find the separating values here, m square plus 4 equal to 0. That is possible roots are m square equal to minus 4. So the roots are plus minus 2 of I as complex roots or imaginary roots here. Then we know that how to write CF in this case. C1 cos 2x e raised to alpha x, real part is 0, e raised to 0 is 1. C1 cos 2x plus C2 sin 2x. Now we concentrate to the method of finding particular integral here. X upon f of d equal to x sin x upon d square plus 4. So the rule in this case is, this is to be defined as follows here: x upon v upon f d minus of this 2d upon this. So what is the value of the function here? This you will use here. This you are keeping as. Now by writing x minus 1 upon d square plus 4. So differential is this sin x. How can you find the integral, particular integral of sin x is d square equal to minus a square, that is minus 1 plus 4. That is, you can obtain here x minus 1 upon d square plus 4 of d sin x upon plus 3. So by writing this, applying this is this, multiplying inside. So x sin x upon 3 minus of 2d 1 upon d square plus 4, 2d of sin x upon 3. So the differential of sin x is cos x upon 3, 2 as it is. Then how can you find the particular integral of cos x or sin x? Rule is same, by putting minus a square, that is minus 1 plus 4. So this gives to a first term as it is x sin x upon 3 minus 2 upon 3 as 1 upon minus 1 plus 4 of cos x upon 1. That is, on simplification, this gives to you the particular integral is x sin x upon 3 minus 2 upon 9 cos of x. Hence, the complete general solution of given problem is y equal to cf plus pi, just by adding these two values here, by putting first cf values, then putting particular integral value here. Let me concentrate on the next example as fifth number question, d square minus 4 of y equal to 2 raised to x. Again, you are having the same strategy by comparing standard forms, then by writing auxiliary equation, and then by finding the roots of this a plus b a minus b. So the roots are plus 2n minus 2. Then the roots are different and real. Then we write on this basis the complementary function is c1 e raised to minus 2x plus c2 e raised to 2x. Now you are going to find its particular integral here. 2 raised to x upon d square minus 4 is the value of the function. Now one rule you will know that if you are having base number power where the power is variable, then you write express in exponential form, because we do not know the particular integral of this case, so we have to convert into our exponential form by applying this rule here. So this gives to you log of 2 of x upon d square minus 4. So in place of x d in the denominator you put a is log of 2, so it is to log of 2x upon log of 2 whole square minus 4. That is, what is this? This you can write again into original form, is 2 raised to x upon log of 2 whole square minus 4. Hence the complete general solution of your given problem is obtained by adding up all both the values cf plus pi. Now we concentrate. Let we see one more examples on the same topic here by comparing with this standard form. Whatever the question is given to you, find out f of t equal to this and capital X equal to x e raised to x. So therefore writing the auxiliary equation m square minus 3m plus 2 equal to 0. So the roots are 1 comma 2. That is, these roots are real and different. You write down on the basis as cf, and then you concentrate the particular integral here. So 1 upon d square minus 3d plus 2 of x plus e raised to x. So is 1 by 2 of separating this 1 minus of, by taking lowest degree term is common, that is 2, and then by expressing in the form as in this pattern here raised to minus 1, whole factors shifted to numerators into multiply by x, and this keeping as it is here. So now by multiplying this inside this gives to 1 by 2 of x minus 3 by 2 differential of dx with respect to first derivative is 1, and then you are getting this value here x of this 1 by 2d minus 3 of e raised to x, because when you are putting this value you are getting the 0. So when you apply exponential case, you are getting 1 plus 2 is 3 minus 3 is 0. So you have to apply case of failure. Case of failure says that multiply by x and numerator keeping as it is, differentiate denominator with respect to d. So the differential of denominator is 2d minus 3 and then e raised to x. Now you are going to put the value of d equal to 1. So 2d minus 1, that is you are getting minus 1. So this gives to you 1 by 2 of x minus 3 by 4 and minus x into e raised to x. So this is the particular integral in this case. Hence the complete general solution of your given problem is obtained by writing cf plus pi as dependent variable is y equal to this, by putting cf and by putting the value of particular integral. Now we concentrate the how can you solve the linear differential equation here. Let me understand their basic tools here. So there are two types of homogeneous linear equations which can be reduced to the linear differential equation with constant coefficient by convenient substitutions. So that our first category is Cauchy homogeneous linear equation. an equation is of the type x raised to n d raised to n upon x raised to n a1 of x raised to n minus 1 dn minus 1 upon dx की power n minus 1 plus dot dot dot, this type of differential equation having variable coefficients. So and while a1 a2 n be the constants, so is called a Cauchy homogeneous linear differential equation. Now we concentrate how can you solve this category of problems, what are the various steps. Let me see these steps one by one. Equation 1 can be reduced to a linear equation with constant coefficient by using the following steps. So first step is put x equal to e raised to z, so on taking log on the both side, and then on differentiating with respect to x, differential of log x is 1 by x equal to dz by dx. Now you will find the value of dy by dx equal to dy by dz into dz by dx, that is on putting the value of dz by dx is 1 by x into dy by dz. So that is you write down in operator form here x multiplied by left side, so x dy by dx equal to dy by dz, that is this can be written as d into y, as here d equal to ddz. Now similarly we can obtain the value of second order derivative as x2 of d2y by dx square equal to d into d minus 1 of y, and similarly you can find x cube in case of x cube. One more factor here or introduces, so d into d minus 1 d minus 2 over y, and so on. We can continue for nth derivative case, so x की power n upon dn y upon dx की power n d into d minus 1 up to this. जब डिग्री 3 है तो 3 फैक्टर्स, जब यू आर हैविंग n फैक्टर्स तो n टर्म्स हैविंग द वैल्यू इज माइनस n प्लस 1. एज फॉर थर्ड डिग्री यू आर हैविंग थर्ड ऑर्डर केस माइनस 3 प्लस 1, माइनस 2 को आप लिख सकते हैं माइनस 3 प्लस 1, एंड 2 के केस में आप इसको लिख सकते हैं माइनस 1 को यू कैन राइट हियर माइनस 2 प्लस 1 दैट इज माइनस 1. सिमिलरली इन प्लेस ऑफ n के केस में लिखेंगे माइनस n प्लस 1. So now in the step number 2, on putting these values in the given equation, then it will reduce into constant coefficient in terms of independent variable z. So now find the complete solution by using the method as dependent variable y equal to c plus pi. And in the final step, when you will get the general solution, you replace z by log x. Now we concentrate one more category of homogeneous differential equation. It is called by Legendre's, so therefore it is called Legendre's differential equation. Only the change is in place of simply alone x, here we have the linear factors as ax plus b. So ax plus b is repeated in each derivative terms, and in excluding this having terms dependent variable terms and the function of independent variable x. So is called Legendre's homogeneous linear equations where a1 a2 n are constants and x is a function of x, small x. Now again we concentrate the method analogous to our previous case to solve this type of problems. First your step is to solve this putting x in place of x, here putting ax plus b equal to e raised to z by taking log on the both side, and then again by differentiating with respect to x. So its differential is, first you differentiate log function, so 1 upon x plus b, then you differentiate inner function x plus b, so differential of x plus b is a, so this gives to you a upon x plus b, and differential of z with respect to x is dz by dx. Therefore now you can find dy by dx as similar to previous case dy by dz into dz by dx. So what will be the value of dz by dx is a upon ax plus b of dy by dz. And next we are going to multiply this or shift it to left side, ax plus b of dy by dx equal to a into dy by dx. This you write again in operator form, a into d of y. Similarly you can find for second differentiation, for second time when you repeat this method, and you will get a2 of d into d minus 1 of y. Then in third phase you will get one more factor adding and so on up to n. There we are being n factors minus n plus 1 d minus n plus 1. Therefore, on putting all these values in equation number 1, you will get a constant coefficient equation with in terms of independent variable z. Find the complete solution, and then finally you put or replace z by log of ax plus b. Let me see an example on this topic here. Suppose this is a question is given to you, x2 of d2y by dx square minus x of dy by dx plus y equal to 2 log of x. So first of all, you understand the category of problems. Of course, this is linear differential equation because the derivative and dependent variables are appearing in separate terms with degree or power 1, and it is second order, and with variable coefficient is x simply. So this is of our first type category. So in order to solve this category of problem, we know that the method is put x equal to e raised to z, so that log x equal to z, therefore 1 by x equal to dz by dx. Hence dy by dx equal to this values, dy by dz into dz by dx equal to 1 by x into dy by dz. x से इधर लेफ्ट साइड में मल्टीप्लाई करेंगे, so this gives to x dy by dx equal to d of y. Similarly, we can obtain this value here. Then on putting these values in the given equation 1, then it will reduce into this pattern here, d square minus 2d plus 1 over y equal to z. It is linear differential equation with variable coefficient of second order. So therefore, first we find its complementary function. For this, you have to write here auxiliary equation is m square minus 2m plus 1 equal to 0. So find out the roots of this quadratic equations. This is an expansion of a minus b whole square. So roots are 1, 1, that is you are getting the repeated roots. Then in this case, since you are having independent variable not x, you have z, you will take in place of x z. So c1 plus c2 z into e raised to z. Now you find the particular integral in this case, as you are having the algebraic function is 2z upon d square minus 2d plus 1. So first of all, you write this expression in the pattern here, 1 minus of, by taking minus common, d 2d minus d square all raised to minus 1 of dz. Now you apply this binomial expansion for this negative index. So power is 1, so you write two terms, so 1 plus 2d minus d square plus dot dot dot. So now applying this inside this, this gives to you z, 1 into z is z, then 2d z minus d square of z. Now you write here 2 plus differential of z with respect to z is 1, so 2 into 1 is 2. So then 2 times when you differentiate z with respect to z, the answer is 0. So that's why ultimately you are the particular integral in this case is 2z plus 2 से मल्टीप्लाई करेंगे, 2 2 4 होगा, तो 2z plus 4. Hence the complete general solution is CF plus PI dependent variable equal to C1 plus C2Z e raised to Z 2Z plus Z. Now converting or reducing Z in terms of X by putting our substitution here, Z equal to log X. So in place of this you are putting this, so 2 log X plus 4 here. Now we take this one more examples on this topic here. It is of the second category, in which the multiples are, the variable coefficients are ax plus b, that is 2x plus 1 whole square. So this belongs to our second category. Therefore you are using this substitution here, 2x plus 1 e raised to z, so that log of 2x plus 1 by taking logarithm on the both side and then differentiating with respect to x. So differential of log x is 1 by x, that is, and then into 2x plus 1 का differentiation होगा 2 upon 2x plus 1 dz by dx. So now you can find the value of dy by dx equal to dy by dz into dz by dx equal to 2 upon 2x plus 1 of dy by dz, that is 2x plus 1 of dy by dz into dy by dx, 2 into dy by dz into 2 of d of y, where d equal to d upon dz. Similarly, we can obtain this value here, 2x plus 1 whole square d2 by dx square equal to 4d into d minus 1. There is an addition of one more factor d minus 1. So just multiplying this inside this. In this question you are having second order derivative terms only, so only this derivative replacement is just required. Then on putting this into this, after simplification, this gives to you d square minus 2d minus 3 over y equal to 3 upon 4 of e raised to z minus 1. Now you can write first the auxiliary equation m square minus 2m minus 3 equal to 0. Just finding the roots of this equation. Factors are m plus 1 m minus 3 equal to 0, that is m equal to minus 1 and 3. Now roots are the real and difference. Then you know that how can you write the CF? CF is c1 e raised to a minus z plus c2 e raised to 3z. Now you concentrate to find the particular integral here. So 3 upon 4 as multiples, e raised to minus z upon d square minus 2d minus 3. So 3 upon 4 taking outside, and then you separate this. E raised to z is different function, 1 is different function. So d square minus 2d minus 3, and by taking a lowest degree term common, that is minus 3 is common. So this gives to you minus of d square minus of 3 minus 2 upon 3 or raised to minus 1 of 1, and therefore you are putting this values here 3 upon 4 e raised to d equal to 1. जहाँ डी है उसकी प्लेस पे 1 रखना होगा, बिकॉज एक्सपोनेंशियल में z का कोफिशिएंट 1 है, तो ये हो जाएगा 1 स्क्वायर माइनस 2 इंटू 1 माइनस 3 प्लस 1 अपॉन माइनस 1 प्लस 1 अपॉन 3 इंटू 1, बिकॉज द डेरिवेटिव्स टर्म्स आर 0. So that's why only one factor you are getting. One term is 1 by 3 into 1, that is simply this. So just writing this 3 upon 4 minus of e raised to this, after simplification this gives to this. Hence the complete solution is y equal to cf plus pi, where cf is equal to this and pi is already calculated here. Now you substitute the original value of z in terms of x. That is y equal to c1 e raised to 2x plus 1 raised to minus 1 plus c2 e raised to 2x plus 1 whole cube of minus 3 upon 16 as 2x plus 1 plus 1 by 4 here. This equation you will obtain here. Now we come to the solution of simultaneous differential equation, simultaneous linear algebraic equation. Here as a fifth word of this unit is, it is first we understand its introduction. Important. Ordinary differential equation arises at the time in which there are two or more dependent variables and a single independent variable, usually the time t. We consider here only a system of linear differential equation with constant coefficient, the solution of which can be obtained by reducing to the solution one or more separate equation, just analogous to algebraic system of linear equation. The method is well explained by the following examples. So this is the example here. Solve the simultaneous linear differential equation dy by dt dx by dt plus dy by dt plus 2x plus y equal to 0, and the second one is dy by dt plus 5x plus 3y equal to 0. So also find the particular solution by satisfying these initial condition x equal to 1 and y equal to 2 when t equal to 0. So first of all you write down the given system of simultaneous linear algebraic equation in our operator form d plus 2 of x plus d plus 1 of y equal to 0, call it by 1, and second one you also write here 5x plus d plus 3 over y equal to 0, where d means derivative as differential operators. That's why we first convert the given differential equation into operator form as an algebraic form. And now as we know that how can we simplify system of linear algebraic equation by elimination methods. So you have to make either the coefficient of x common or the coefficient of y to be common. So that's why you have to make the common multiples, you have to select. So now operating the equation 1 by d plus 3 and the second one by d plus 1, that is we want to cancel y and then subtracting to them. So this gives to you d square plus 1 over x equal to 0. Now this is the differential equation of higher order with constant coefficient. How can you find its auxiliary equation here? M square plus 1 equal to 0, that is roots are m equal to plus minus I, that is imaginary roots. Then we know that how can we write in this imaginary roots CF equal to C1 cos of t plus C2 sin of t, and the particular integral is to be 0 because right hand side in this equation is 0. So that's why you are getting the complete solution as the value of one independent variable is x equal to CF plus pi, that is C1 cos of t plus C2 sin of t. Now by using this value in the any one, and or you can repeat this same process. So now eliminating dy in equation number 1 and 2 by subtracting from 1. So this gives to you y equal to 1 by 2 of dx minus 3 by 2 of x. That is, now you are putting the value of x in place of x. So 1 by 2 of d of c1 of cos of t plus c2 sin of t minus 3 by 2 c1 cos of t plus c2 sin of t. That is y equal to 1 by 2 of minus c1 sin of t, because the differential of this is cos t is minus sin t plus c2 cos of t minus 3 by 2 of c1 cos of t plus c2 sin of t. So this is your y. By solving this, now by applying the given initial condition here as x equal to 1 and y equal to 2 when t equal to 0, from equation number 4 you will get c1 equal to 1, and by equation number 5 you will get c2 equal to 7. And then on substituting this in values in 4 and 5, you will get the particular solution here of the given system of simultaneous algebraic equation. Thank you very much.